Modern science has major epistemic flaws that make its conclusions extremely unlikely to be true. Okay, this graph represents your theoretical model. As your theory increases in complexity, it gains nuance and predictive power, and we're going to call this resolution. This is the explanatory power of your theory. Most of this model doesn't come from direct observation. We have to construct it through deduction and inference, which is an imperfect process. So we can end up with something that predicts outcomes and appears sophisticated but isn't necessarily true. We're going to use the word fidelity to describe the degree to which the model actually matches up to reality, or whether it's describing something fundamentally real and true. We often come up with multiple competing theories that explain the same phenomena with equal resolution, but logically we know that they can't all be true. Whether any particular theory is true or not is ultimately up to your own discernment, which makes fidelity something of an unknown quantity. The best we can do here is assign it a hypothetical probabilistic value. But generally speaking, we can safely assume that as resolution increases, fidelity naturally decreases. The further your theory gets from first principles and direct observation, the less likely it is to accurately reflect reality, even if it works. People often misunderstand Occam's razor. It doesn't mean the simplest answer is the best. It means the explanation that requires the fewest amount of assumptions is most likely to be correct. You can explain anything if you make enough assumptions, but every assumption lowers fidelity. Modern science prioritizes resolution over fidelity. It needs theoretical models to be functional, but not necessarily true. So let's take a little bit of a closer look at this chart here and see what's actually going on. At the very bottom we have reality itself, the thing we're observing as it is in its natural state, before we apply any abstraction or analysis. So at this point our model has 0% resolution and 100% fidelity. It just is what it is and we can't explain it. But we can't study what we can't describe, so we build tools. Instruments that translate things we can't directly observe into measurable values. These values are simply abstractions of the real thing. The thing we're measuring isn't itself a number, but we convert it into one so we can reason about it. The goal is to find patterns in the data, but that depends on having the right tool for the job, properly calibrated, and interpreted through the right axioms. Instead, data is often filtered through pre-existing models, and if it doesn't fit, it's treated as error or noise. The tool presumably has some margin of error, so we attribute the mismatch to the tool rather than the model. Then we start categorizing recurring patterns as organisms or substances or processes, entities we can't directly observe, but we infer through filtered data. Then we develop higher-level theory about how these inferred entities behave and interact. Each layer of inference is built on the validity of the previous one, which provides compounding exponential uncertainty that lowers fidelity. A high-fidelity epistemology works from the ground up from axiom to theory, using strict logical standards at every step. Modern science, by contrast, tends towards top-down epistemology. Once a theory is established, it can then be adjusted infinitely through post-hoc reasoning to keep it intact. Logically, if a model fails, the premises are false. But scientifically, you can just keep tweaking the model until it fits the observation. Take dark matter, for instance. It isn't even clearly defined. It exists purely to patch the gap between Newton and Einstein's math and what we actually observe. It could simply be that Newton and Einstein were wrong, but that's not even considered because the goal is to make the model work. And that's why post-hoc justification is fallacious, because it preserves functionality at the expense of fidelity. And then ego majorly amplifies the problem, because once you claim ownership over a theoretical model, it becomes yours or your career depends on it, you'll defend it. Or at least you're highly likely to if your pride outweighs your curiosity. The deeper your understanding of a flawed system, the harder it is to let it go, and the more likely you are to employ post-hoc justification to keep it. And up to this point, these are just natural pitfalls of any epistemology: abstraction, bias, ego. But where modern science truly fails is its validation system. Logic is the foundation of epistemology. It's the only tool we have to minimize bias and preserve fidelity. Sound reasoning is synonymous with truth. But the process of scientific validation doesn't move upward from logic. It flows downward from authority. It goes from authoritative, credentialed sources to peer review to consensus. No part of this system ensures sound reasoning. Appealing to credentials is definitively an appeal to authority fallacy, and peer review and consensus are bandwagon fallacies. Experts agreeing doesn't make something true because having credentials doesn't make you right. You would think a bunch of logical fallacies would make for a poor validation system. It wouldn't be my first choice. Logic appeals to an external source, reality itself. But function depends entirely on personal motivation. Consensus flows downward from authority, so authority ultimately dictates what counts as valid science. And I don't trust the motivation of authority enough to accept this as a legitimate validation process. Trust the science and settled science is nonsense. It's just not how science works. These phrases elevate obedience over understanding, and they assume that authority equals honesty and that institutional motivation aligns with truth.